In this section, we'll be taking a look at the graphs of sine and cosine functions
together. So now recall our unit circle. And recall that the points on this unit circle where the terminal ray of an angle crosses the unit circle gives you the value of cosine of that angle theta and sine of that angle theta. As an example, let's say I have an angle in standard position, so I know the initial ray is this one. The terminal ray makes an angle of 45 degrees, of 60 degrees. Now, let's say that terminal ray is followed all the way until it intercepts the unit circle. The place where it intercepts the unit circle is 1/2 comma root 3 over 2. All right? So these two values give us the cosine of 60 degrees and the sine of 60 degrees in that order. All right? Now, up to now, when we define sine and cosine, we define them together at the same time. But there is something to be learned by looking at these values one function at a time. What we're going to be doing in this section is we're going to be graphing the sine function entirely on its own, meaning without worrying about what's happening with this value, which gives us the cosine of the angle. Likewise, we're going to be graphing just the cosine, where we're going to ignore these y values, which give us the sine of that angle theta. All right, so we're going to be coming back to this circle over and over again to get some values, but we're going to be graphing them one at a time, meaning we're not going to graph these points this way where you have an angle, you have an x value and a y value associated to that angle. Instead, what we're going to do is we're going to graph these as functions. The angle, the function of the angle will give us this number, or separately, the function of the angle will give us this number. Okay, so we're going to do these as two separate functions. And let's begin with the sine function. So we're going to begin by graphing f of x equals the sine of x. Now, this can sometimes get a little confusing because, of course, we're used to saying, well, x is the x value on the unit circle, and y is the y value on the unit circle. Here, they're using x in a different context. They're saying x is the number that you're plugging into the sine function. If you get used to that, that's great. However, if you prefer, many people prefer to write it this way. That way they're still realizing, oh, theta is that angle. So here what you're saying is you give me an angle and the function gives me back the sine of that angle. Not the cosine. I don't worry about this one. I'm only worrying about these entries here. Okay, so in the textbook, they'll write f of x equals sine of x sometimes. Other times they'll write f of theta equals sine of theta. Either one is fine, but I want to start off with theta to make it look a little more familiar to what we've been doing so far. Okay, so the sine function, in fact, all of the trig functions, which we'll be seeing throughout this chapter, are what are called periodic functions. So before we graph this, let's remind ourselves, let's give a definition. Let's begin with a function. Let f be a function. If f of x, and of course this can be anything including this theta here, but if f of some argument is equal to f of that same argument plus n times p, where n is every possible integer, positive or negative whole number is any integer, and x and p are real numbers, then f is called the periodic function. Well, actually, this is bad grammar. I should say where n is any integer. Here, that's bad grammar. Let's go ahead and say it this way. Where n is any integer, x is any real number, so it doesn't have to be an integer, it could be a decimal, a fraction, anything we like, any real number, and P is some real number. So what's the difference? Here, this x can be any x. Here, this P is going to be a specific number. So it doesn't have to be an integer, but it is going to be some specific number or maybe some specific set of numbers. We'll see the examples of that here in a moment. X is any real number and P is some real number. Then then F is a periodic function. And the smallest possible value of P is the period of F. Okay, so there's our definition of periodic function. Okay, looking at your unit circle, it's obvious that sine and cosine repeat over and over again. If I have the angle 30 degrees, I can say, what's the cosine of that? Well, it's root 3 over 2. Now, what if I go all the way around and I end up at 390 degrees? What's the cosine of that? Well, root 3 over 2. What if I go all the way around again and I end up at 750 degrees? What's the cosine of that? Well, again, root 3 over 2. Notice that if I go all the way around, I end up with the same value. Well, what does it mean to go all the way around? Well, in degrees, it means I added another 360 degrees. Or if I'm talking radians, I've added another 2 pi radians. That's what we mean by a periodic function. It means that if you have a value that you get from that function, you're going to keep getting the same value over and over again as long as you add the same amount. In this case, either 360 degrees or 2 pi radians. We're going to see that a little bit more apparent when we actually create these graphs. Okay, so we're going to graph f of theta is equal to sine of theta. To do that, we're going to start off with a small list of values, and we're going to get them all off the unit circle. Here, I'm going to go ahead and do this in radians. You can do it in degrees if you like, but many of the problems that we see in this course are done in radians, so I'm going to go ahead and just follow suit. So here, if I have the 0 radians as my angle, then I'm starting with graphing sine. So the sine of 0 radians is 0. Okay, so here I'm going to say here's theta, and here's sine of theta. Now I'm just going to fill in some numbers. So 0, 0. Pi over 6, well, if I take the sine of pi over 6, I get a half. Okay, so pi over 6, 1/2. And then pi over 4, it's going to give me root 2 over 2. And then pi over 3 is going to give me root 3 over 2. And then if the angle is pi over 2, the sine of that's going to be 1. Okay. If I keep going, my angle is the angle 2 pi over 3. I'm going to get root 3 over 2 as my sine. If I have 3 pi over 4, I'm going to get the sine of that is root 2 over 2. If I have 5 pi over 6 radians as my angle, the sine of that is 1/2. And if I have the angle pi, I end up with 0 as the sine of that. The sine of pi is going to be 0. I'm going to keep going all the way around until I go all the way around the circle. Okay? So that's going to be pi. Next I can do 7 pi over 6. The sine of that is going to be -1/2. And again, I'm just grabbing these off this unit circle. All right, here's my angle, 7 pi over 6. The terminal ray of that angle crosses the unit circle here. So the sine of that angle is this second entry, which is -1/2. Oh yeah, -1/2. Okay. If I keep going, That's going to be the angle 5 pi over 4, and the sine of that is negative root 2 over 2. If I use the angle 4 pi over 3, that's going to be the angle negative root 3 over 2. If I use the angle 3 pi over 2, that's going to give me negative 1 as the sine of 3 pi over 2. The sine of 5 pi over 3 is negative root 3 over 2. The sine of 7 pi over 4 is equal to negative root 2 over 2. The sine of 11 pi over 6 is equal to negative a half. And all the way around the unit circle, once I get back to 2 pi, remember 2 pi means you went all the way around and you're back to where you started. So here, this is going to be the same as where we started. Sine of 2 pi is 0. Notice there's a lot of symmetry here. This is the same as that one. 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 Same thing over here. This is the same as that one, and that one, and that one, and that one, and that one. And of course, that's to be expected because of the symmetry of the circle. So now let's graph these. Notice that we don't include cosine of theta at all. This graph will only relate the angle to the sine of the angle. The cosine is nowhere to be found. So let's go ahead and graph this. All right, so let's see here. So let's go ahead and graph right here. We know that the maximum value that the sine of an angle can have is positive 1, and we know the minimum value can have is negative 1. So here we don't need this graph to go very high up or very far down. It's got to be somewhere between here and here. All values of the sine of theta are always going to be between -1 and 1, as you can see off the unit circle. All right, so let's go ahead and graph a few of these points. Okay, if theta, and here this is going to be theta, this is going to be my angle, and again I'm doing it in radians, and this is going to be the sine of theta. Okay, so if theta is equal to 0, sine of theta is also equal to 0. Okay, so that's a simple enough point, 0, comma 0. I'm starting at the origin. Okay, now if I have theta is pi over 4, I'm going to get sine of theta is root 2 over 2. Root 2 over 2 is an exact value. However, if we're graphing, we might be better off with a decimal here, just an approximation. The square root of 2 divided by 2 is about 0.70, about 0.71. So just under 3/4. Okay, so if my theta is pi over 4, I'm going to go up almost all the way to 3/4. So right around there. Okay. If my angle is pi over 2, well then my sine of pi over 2 is going to be 1. So from here I'd go up straight to 1. At 3 pi over 4, my sine would be root 2 over 2, which is the same number that I had before, just a little bit under 3/4. And at pi, well, the sine of pi is 0. So I'm back down here. If I keep going, notice I'm skipping a few because I don't have the room to graph all of them, but even graphing every other one like I'm doing is still going to give you a nice pattern. 5 pi over 4, the sine is negative root 2 over 2. So in other words, about negative 3/4, give or take. So here I'm going to go down 1, 2, almost to negative 3/4. 3 pi over 2, the sine of 3 pi over 2 is negative 1. So from here I'd go down to negative 1, right about there. At 7 pi over 4, I get negative root 2 over 2, which is negative 0.71, give or take. So I'd go down almost all the way to negative 3/4. And if my angle is 2 pi, then the sine of 2 pi is 0. So now I'm going to go ahead and connect these dots. Note that these are all points that are coming off of the unit circle. You wouldn't expect these to be connected with straight lines. They're along the outer edge of a circle. Same thing here. You don't expect these to be connected with a straight line. The curve forms more of a wave pattern. So it comes up and down in a nice smooth wave. And this is the graph of the sine function. Well, not quite. Because notice you could keep going. I could have an angle bigger than 2 pi. Even though on the unit circle 2 pi means I'm done, it doesn't really mean I'm done. I could now say 13 pi over 6. And 13 pi over 6 also has a sine, which is Well, it's going to turn out to be 1/2. This doesn't mean we're done. It just means that once we reach this, we're about to start over again. So if you were to zoom out and graph this like this, you would say, okay, here's 0, here's pi, here's 2 pi. This would go up, come back down, go down, and then come back up. But you wouldn't be done. It would simply start over again. From here, you would just have another copy of this wave. It would go up, come down. That's 1 pi, 2 pi. This next one would be 3 pi. It would come down and then come back up, 4 pi. And again, and again, and again, forever. The graph of the sine function goes on forever. There is no end to it. However, we don't usually graph the whole thing. We typically graph just one portion of it, the part from one beginning to one end of one cycle, one time around the unit circle. That's what we mean by a periodic function. Notice it keeps repeating over and over again. Incidentally, it repeats this way too. I can also have negative angles and let it repeat on forever this way. Notice that if I plug in, for example, this point right here, if I said pi over 2, notice that that's not the only time that that happens. If I just wait a while, eventually it happens again. And in fact, if I wait another while, it happens again and again and again. Okay, well, how long does it take before it happens again? Well, let's see. This was pi over 2. And this one right here is halfway between 2 pi and 3 pi. Okay, so that's 5 pi over 2. Well, the distance between pi over 2 and 5 pi over 2 is 2 pi. So the distance between a point and when it happens again is 2 pi. And same thing over here. The distance between here and here is 2 pi. When something happens, it'll happen again as long as you wait this much. Right? And again, if you wait again by this much, it'll happen again and again and again. This is called the period of the function. It's how long it takes before you can expect that point to happen again. Sometimes it's called the period length, how long the period is. However, we can just say it's the period. Okay? Notice we could say the period is 4 pi, right? After all, it happens here. And if I wait this long, it'll happen again. Well, yeah, but by definition, the period is the smallest possible value. So here you say, okay, if I wait 4 pi, it'll happen again. Yeah, but it would happen if I waited 2 pi. I want the smallest amount before it happens again. Notice that there's nothing special about these points up here. If I said, for example, this point down here, if I wait 2 pi, hey, it may be a different point, but if I wait the same amount, notice those are going to be the same length. If I wait the same amount, that point will also repeat. That's, again, going back to the definition, this is true for x being any real number. If you pick any point along this curve, if I pick, for example, this point, if I wait for this to go 2 pi units forward, that point will happen again, and again, and again, and again. Without going through the entire plotting of this, let's go ahead and just show the illustration of what the cosine function is going to look like. If we repeat the process of taking points and plotting them, here are the graphs of sine of theta and the graphs of cosine of theta. Note that even though they are two graphs, and they clearly do have two different sets of points on here and different locations, we do repeat a lot of the same values. Because, of course, all of them are coming off of values from the unit circle, where really these three numbers are the only ones that keep appearing, right? 1/2, root 3 over 2, and root 2 over 2. So even though they are different functions coming from different parts of this unit circle, a lot of the numbers are repeated anyway. So here you'll notice that, yeah, the graphs are different, but they do kind of look the same. They have a lot in common. Note that your sine function begins here at the origin, goes up to its maximum, the highest point, and it does that a quarter of the way through its period. Then it comes back down. Halfway through the period, it comes back to the x-axis. It reaches its minimum when it's 3/4 of the way through that period, and it comes back to the x-axis at the end. Okay? So here you can think of this as being cut up into 4 regions: first quarter, second quarter, third quarter, and fourth quarter. Yeah? It starts off at 0, maximum 0, minimum 0. In a bit, we're going to start modifying this. We're going to start saying, okay, what if it's not sine of theta? What if it's sine of 2 theta? What if it's 5 times the sine of 3 theta? What if it's 1 minus the sine of 6 theta plus pi over 2? That's going to change the graph. But this basic structure will remain the same. It'll be, imagine cutting this into fourths. You're going to start up to the maximum, down to the, then down to the minimum, and then up. The cosine function looks more like this. It starts at its maximum. Notice over here we start at 0. Over here it actually starts at 1 at its maximum. Again, imagine cutting this into quarters. A quarter of the way through, you hit the x-axis, or I guess in this case the theta axis. Then you hit the minimum halfway through your period, and then you come back to the axis 3/4 of the way through, and then you end right back where you started at its maximum. Okay? Both of these are smooth waves. And of course, these are both periodic functions, so this wave does keep on going forever in both directions. Same thing here. Once you get here, you would simply restart this wave over again. This is not a full graph of sine or cosine function because, of course, it is missing a lot. It goes on forever in both directions. However, when you see a graph, you usually see this part or some version that comes from this part. This is called the central period of the sine function. The central period is the one that we graph from points off the unit circle. So the central period of the sine function begins at 0 and ends at 2 pi. Starts at theta equals to 0, and it ends at theta is equal to 2 pi. It's also going to be true for the cosine of theta. And for f of theta equals the cosine of theta. So for both of these, it starts at 0, and it ends at 2 pi. Note that that means that every time you add another copy of 2 pi, your wave starts over again. And so that means that's the period of the sine function. Likewise for cosine. Going back to our definition of a periodic function, what that means is that the sine of x is equal to the sine of x plus n times 2 pi, wherever n is just some integer. And the same thing will be true for cosine. So note from the definition of a periodic function combined with these graphs, we can write that the sine of x, or I'll continue to use theta, the sine of theta is equal to the sine of theta plus n times 2 pi. Often that's written as 2n pi. You can write it as n times 2 pi. However, in just about every book you'll ever see, including this one, they write it as 2n pi. What that means is, as long as you plug in any integer right here, these two are equal. So sine of theta is equal to sine of theta. Or sine of theta is equal to sine of theta plus 2 pi. Or sine of theta is equal to sine of theta plus 4 pi. Or, well, anything. Plug in any integer you like right here, positive or negative whole number, and the sine of theta will equal to that. Same thing is true for the cosine. The cosine of theta is equal to the cosine of the angle theta plus n times the period length, which again is 2 pi. And in most books, including this one, it's usually written as theta plus 2n pi. From these graphs, we can also note a few other things about the sine and the cosine as separate functions. We've mentioned this already before from the unit circle, and this simply reinforces that. If you have f of theta is equal to the sine of theta, this is a function whose domain is all real numbers. Notice, this keeps on going forever and ever to the right and forever and ever to the left. So the domain of the sine function is every real number from negative infinity to infinity. But the range is limited, a maximum of 1 and a minimum of negative 1. And the same thing is true for the cosine function. This goes on forever in both directions, so its domain is infinite, but its maximum and its minimum are between 1 and minus 1. So here f of theta equals to the cosine of theta. This further reinforces that the domain of this function is all real numbers, whereas the range of this function is simply the values between minus 1 and 1. Another thing to note is that if I have the cosine of a value theta, and I have a cosine of a value negative theta, so for example, if that was pi over 3 and negative pi over 3, or pi over 2 and negative pi over 2, if these are the same number but with an opposite sign, these are going to be equal to each other. You can tell that by looking at this graph. It might be a little easier if we zoom out just a bit. So consider the graph. Here's the central period. Starts at a maximum, comes down to the axis, then to the minimum, and then back to the axis, and then back up to the maximum. But of course, this keeps on going, and it goes on forever in both directions. So here what I'm going to do is I'm going to draw another copy of this, but instead of drawing it to the right, let me draw it to the left. So it's going to start off and end at a maximum. It's going to hit the minimum halfway between the maximums, just like this. Well, notice if I have a positive theta or a negative theta, as long as I'm the same distance away from the axis, I still end up with the same y value. So here if I have positive pi over 3 or negative pi over 3, it doesn't matter. The y value is still the same. The height is still the same. And same thing over here. If I have this positive theta or this negative theta, it doesn't matter. I still have the same cosine of theta. So here, regardless of whether I have a positive or a negative angle, the cosine still gives me the same result. If you think back to college algebra, what do you call a function where if you substitute a positive or if you substitute a negative, it makes no difference? Let's call it an even function. So here, note that the cosine of theta is an even function. You can do the same thing. You can compare the graph to note that the sine of theta, if you take the negative angle, that's the same as saying the negative of the sine of theta. Or in other words, here, if you put a negative in here, that's the same as if you put a negative on the outside. All right? That's different from this one. Here, with or without the negative, it makes no difference. Here, you still need the negative, but what doesn't make a difference is whether the negative is on the argument or whether the negative is outside of the function. If you think back to algebra, the name for a function like that is called an odd function. So the sine of theta is an odd function. For now, those are just names. You know, there's nothing even or odd about these in terms of like numbers. Usually when you think of even, you think of even numbers, 2, 4, 6, 8. Odd, you think of odd numbers, 3, 5, 7, 9. Obviously, there's no numbers here in any obvious way. For those of you who follow us onto calculus, eventually the name even and odd makes a little more sense in that context. But for now, don't worry about saying, well, where's the even number? Where's the odd number? You're not going to find one, and that's okay. For now, just consider these as names. This is called an even function, and this is called an odd function. And this will help us with some computations later. This is not exactly groundbreaking, but it'll make a few things simpler where, oh, I can ignore a negative from time to time, as long as I'm dealing with the right kind of function. Once we understand what the graphs of f of theta equals sine of theta and f of theta equal cosine of theta look like, we can now modify these. If you think back to algebra, whenever you had a quadratic equation, f of x equals x squared plus 7x minus 12. That was going to be a parabola. And the only difference between one parabola and another is that some of them were wider, some of them were narrower, Some of them were higher up or lower down, or moved left or moved right. And sometimes you even had them and you flipped them upside down, so they were facing in the opposite direction. So this is going to behave the same way. In algebra, you call those transformations. You have dilations, which make things either wider or more narrow, make them taller or shorter. Those are called dilations. You have translations, which move things left or right or up or down. And you have reflections, which flip things either upside down or left to right. We're going to have the same thing here. These functions are going to behave as a basis of something that can be modified using transformations. So let's take a look at some examples of that. Oh, actually, I suppose before I state an example, let me state the generic form. Let's say I have a function f of theta is equal to a times the sine of, oh, I want to use the same characters they use in your book. So I believe they call this b. So a sine of bx minus d plus c. Why they've chosen that order, I'm not sure, but that's the order they've chosen. So whenever you have something that looks like this, notice this is, here, let me use theta still. Let's not use x. Let's keep using theta just to be consistent. We could use x. We can use any letter we like, but just to be consistent, I'll keep using theta. So here, that's f of theta is equal to a sine of b times theta minus d plus c. Okay? This value of a is called the amplitude of your function. And what it'll measure is the distance between the maximum and the minimum. Not the horizontal distance, but the vertical distance. Here, the distance from here down to here. How far is it from the maximum value down to the minimum value? Here, you'll note that from this axis to the maximum, it's one step. Likewise, from the axis to the minimum, it's one step. Here, you can think of this as being 1 sine of theta. If you change that amplitude, it'll change how far up the maximum is, and at the same time, it'll change how far down the minimum is. And we'll see examples of that in just a moment. But for now, that's the title. This is called the amplitude. This value of b is going to cause a dilation. And the dilation that it's going to cause is a dilation horizontally. In other words, it's going to make the wave wider or more narrow. It's going to take these endpoints and it's either going to bring them closer together or it's going to stretch them further apart. Well, how much is it going to do that? Well, this value here tells you the length of your new period. So the period of the function, the period of f, is 2 pi divided by b. So if b is the number 1, well then the period is 2 pi, the way it usually is. But if b is, for example, the number 2, 2 pi divided by 2 is just pi. So now instead of being a period of 2 pi, now it's only a period of pi. The whole thing moves closer together. The whole thing gets narrower. These are responsible for translations. In other words, movements left and right and up and down. So here d, this is going to cause a horizontal shift. You're going to move things either left or right. Another name for a horizontal shift when you're dealing with periodic functions like sine and cosine, this is also sometimes called the phase shift. And this book likes to use those phrases interchangeably. Sometimes it'll say, graph the horizontal shift, or sometimes it'll say graph the phase shift. It just means how far it moves left and right. And this will give you a vertical translation, a vertical shift. The whole thing will either move up or down. All right, so let's begin by looking at what's going to happen with each of these types of transformations. Note that the exact same thing will happen with a cosine instead of a sine. If I replace this with cosine, everything else remains the same. The only difference is here, if I have a function with a sine right there, I'm going to start with this graph and modify this one. If I have cosine, I'm going to start with this graph and modify this one. This one would get taller or shorter, wider or narrower. So the only thing that changes between this being sine or this being cosine is which function do I start with. But once I have a starting function, once I have a starting central period, all the changes to that central period remain the same. So let's take some examples. We're going to graph f of theta is equal to 3 times the sine of theta. Okay. I'm going to go ahead and graph the original function, sine of theta, the parent function, the function that has not been modified, and then I'll go ahead and graph this one that we're being asked for. And that'll just be for the sake of comparison. Okay, so my sine function begins at the origin, 0, 0. I'm not modifying it yet. I'm just graphing the sine of theta. So in fact, let me do that in a different color. So I'm going to start at 0, 0. Now, I'm going to go up to a maximum when this is pi over 2. When this is pi, I'm back to the axis. All right? So here I went up to a maximum, so that must be 1. And then when I get to 3 pi over 2, that's when I'm at my minimum. That's when my central period of the sine of theta is at a minimum. And then finally, when I get to 2 pi, I get back to the axis. Okay, so this is just the graph of f of theta is equal to the sine of theta. The amplitude changes the height of the maximum and the depth of the minimum. It doesn't change anything here. It doesn't change anything along the axis, because here along the axis, the sine of theta is equal to 0. And if you triple 0, well, it's still 0. But notice this sine of theta is equal to 1. So if you triple it, triple 1 is 3. It's gotten a lot taller now. So now instead of going to a maximum of 1, it's going to a maximum of 3. Likewise, here the sine of theta is negative 1. So if I triple that, that gives me negative 3. Notice it just comes straight down to negative 3. Sine of theta is negative 3. And then I come back to the axis. If I connect my dots, I still have the same graph. It should still have the same shape. But now everything's gotten taller. All right. The amplitude tells you the distance from this baseline up to the maximum and down to the minimum. So notice right here, from this baseline, from the average between the maximum and the minimum, this is the distance 3, and this is also the distance 3. Or in other words, it's the amplitude. So right here, from this axis, from the baseline, the line that gives you the average between the maximum and the minimum, you go up by a to find your maximum and down by a to find your minimum. Note that just like in college algebra, if this value is a negative, not only does it change your amplitude, but it'll also cause a reflection. It'll make everything flip upside down. So recall that having a negative number here, aside from changing the amplitude, will do the same thing it did in college algebra, and it'll flip things upside down. So let's say I want to graph, and let me use a different letter here. Let's call this one G. G of theta is equal to negative 2 sine of theta. Well, now, this is going to change my amplitude. From this baseline, I'm no longer going to go up 1 or 3. I'm going to go up 2. Oh, but the negative is going to cause a reflection. It's going to make everything upside down. So instead of going up to my maximum of 2, I'm going to do the opposite. I'm going to go down to a minimum of 2. And over here, I would normally go down to a minimum of 2 here. if this was 2. But because of the negative, everything gets flipped, so now I go up to a maximum. So notice that changes the amplitude. Instead of going up to 1 and down to -1, now I go up to 2 and down to -2, but it also reflects my graph. It changes everything so that it's upside down relative to what it was before. So taller, but also upside down. Where it would normally be at a maximum, it's now at a minimum. Where it would normally be at a minimum, now it's at a maximum. Okay. Now, this part right here, you can think of it numerically as 2 separate actions. You can think of it as a dilation of your period, making things wider or more narrow. And separately, you can think of it as a phase shift, as a movement of your graph either left or right. But it's often simpler to think of both of these actions simultaneously. And here's how we're going to do that. Let's go ahead and graph f of theta is equal, let's stick with sine for now, so sine of 2 theta minus pi over 2. All right. So here we could think of this as 2 separate operations, right, here and here, but it's going to be simpler to do this. Normally, a central period of either sine or cosine begins at 0 and ends at 2 pi. Well, yeah, but that's when that's just theta. If I have sine of theta, I begin when theta is equal to 0 and theta is equal to 2 pi. But here that's not just theta, that's something more complicated. Well, yeah, but still, this should be 0 for me to start my period. And it should be 2 pi for me to end my central period. So the question is, well, what do I have to do to make this 0? Oh, well, let's find out. The central period, I don't know how to spell central period. There we go. The central period will start when the argument, in other words, the stuff in the parentheses, when the argument equals to 0. Meanwhile, the central period will end when the argument is equal to 2 pi. So let's figure out when those two things are going to happen. If I take my argument, 2 theta minus pi over 2, and I set that equal to 0, let's solve for theta. Let me add pi over 2 to both sides. Add pi over 2, add pi over 2. Pi over 2 minus pi over 2 goes away, and I'm left with 2 theta is equal to positive pi over 2. Okay, well now let me multiply both sides by a half. That way half of 2 is just 1, that goes away. And I multiply this side by a half. And so I get theta is equal to 1 pi over 4. Okay, and then I can do the same thing, but instead of having this equal to 0 to start my central period, I can now set it equal to 2 pi to end my central period. So 2 theta minus pi over 2 is equal to 2 pi. Okay, let me add pi over 2 to both sides. Add pi over 2, add pi over 2, and that goes away. And I'm left with 2 theta, because that's gone. And over here, 2 pi plus pi over 2, that's going to be 5 pi over 2. And now I can go ahead and multiply both sides by a half. Half of 2 is 1, which is what I want. I want 1 theta there. And 5 pi times 1 is 5 pi. 2 times 2 is 4. So now my central period doesn't start at 0 and end at 2 pi. Now it starts at pi over 4 and ends at 5 pi over 4. So let's go ahead and graph that. So let's begin by graphing our unmodified function. Let me go ahead and just graph sine of theta so that we can compare. Sine of theta starts at the origin and it ends at 2 pi comma 0. It's going to achieve its maximum at pi over 2. A quarter of the way through, it hits its maximum. Halfway through the central period, it comes back to the axis. 3/4 of the way through, it achieves its minimum. And then it goes back to the axis at the end. Okay, so this is not the graph that we want. This is just the basic graph of the sine of theta. All right, so this is the central period of f of theta equals the sine of theta. Now, using the information that we just computed, our central period for our function should begin at pi over 4. Okay, well, the central period for the sine function is 0, 0. Okay, well, now it's moved over here to pi over 4 comma 0. We should still start at the axis. It's just we've moved over, so instead of starting at 0, 0, now we started pi over 4, 0. Likewise, we're still going to end on the axis, but instead of ending at 2 pi comma 0, we're going to end at 5 pi over 4 comma 0. So right here. So notice, this takes our endpoints and brings them closer together. This point is now here, and this point is now here. You say, well, what about all the stuff in between? Well, we're still going to follow the same pattern. This is the start of the sine wave. This is the end of the sine wave. Remember how that works? That's 1/4 of the way through, halfway through, 3/4 of the way through, and that's all the way through the period. 1/4 of the way through, you're going to achieve the maximum. Halfway through, you're going to get back to the axis. 3/4 of the way through, you're going to hit the minimum. And then you're going to go back to the axis at the end of your central period. So this is going to go up, down, down to the minimum, and then back up. And this is our function. This is our f of x. Oh, so that should be f of theta. This is our f of theta equals sine of 2 theta minus pi over 2. Here we can confirm something about our graph. Note that whatever value this is, whatever the coefficient of your variable is, whether it be x or theta or anything else, whatever this number is, 2 pi divided by that number gives you the period of your function. Well, here that's the number 2. The period of this, I don't know why, I don't know how to spell the word period today. Here we go. The period of this function is 2 pi over that number there. Which is 2 pi over 2. And since those divide away, that just gives us pi. Well, notice that's that distance. The distance between 5 pi over 4 and pi over 4. Well, if you take 5 pi over 4 and subtract pi over 4, that's 4 pi over 4. 5 pi over 4 minus 1 pi over 4, that's 4 pi over 4. Which is just pi. Oh yeah, that confirms that. So if ever you're not certain that you've done that correctly, if you take 2 pi and divide it by that coefficient there, don't worry about that one right now, you can find the length of your central period, and it should match with what you've graphed. If not, something's seriously wrong. And there we go. Here's our graph. Note that from here to here is one period. This should be halfway in between those, and this should be halfway in between these, and this should be halfway in between these. Here, the numbers worked out really rather nicely. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. If the numbers don't work out easily, you can always just average the two numbers together. Because remember, the number that's halfway in between two extremes is their average. So here, if these weren't numbers that worked out nicely on this grid, you wanted to say, okay, well, what is halfway in between here and here? Add these together and divide by 2. That'll tell you the average of the two endpoints, or in other words, the point in the middle. Likewise here, if I didn't know what was in between here, 3 pi over 4 plus 1 pi over 4 is 4 pi over 4, which is just pi. Now if I cut that in half, that's pi over 2. Oh yeah, that's the point halfway in between. So averaging these two will give you the one in the middle. Averaging these two will give you the one in the middle. Averaging these two will give you the one in the middle. That's just a nice computational trick, just in case you ever end up with numbers that aren't quite so nice like that. Okay. Let's take a look at one more example. Let's say we're going to graph f of theta is equal to 2 times the sine of theta plus 1. Okay. Notice this plus is on the outside of my function, not in the argument. So this is going to cause a vertical shift. It's going to move things either up or down, positive being up and negative being down. Okay. So let's go ahead and graph this. So we can go ahead and graph, starting with the just regular sine function. That way we can compare what that looks like compared to our new one. Okay, so normally the sine function starts at the origin, goes up to its maximum of 1 whenever theta is equal to pi over 2. Then it comes back to the axis when theta is equal to pi, reaches the minimum when theta is 3 pi over 2, and then comes back to the axis at the end of its central period of 2 pi. You go up and then down to the minimum and then back up. Okay. This one's a little bit flatter than this one just because I drew it with a smaller scale. It's meant to be the same as this one here. All right, so now this is going to change the amplitude. It's going to change how far up or down it goes. But what this is going to do is it's going to change the position of this graph vertically. What you can think of this is what's telling you what's happening to the axis. So these points here are on the axis. By adding 1, it's going to move these points up 1 step. 1, 1, and 1. But now these points are going to be governed not only by this value, but also by this value, where this value tells you the change to the amplitude. Now, the simplest way to do that is to say, well, I remember that the amplitude tells you how many units away you are from the baseline, from the axis. Well, yeah, but my points on my axis, these 3 points, have now moved up. So this number 2 tells me that from this line, in other words, starting from where f of theta is equal to 1, I'm going to go up that many units and down that many units to find my maximum and my minimum respectively. Okay, so I expect my maximum to be a quarter of the way through the period. There's my baseline, and now my amplitude tells me that from this baseline I go up 2 steps. My minimum should be 3/4 of the way through the central period. Here's my baseline. So from here, my amplitude tells me that my minimum is 2 steps down from this point. 1, 2. So now I can connect these points, and it's still going to connect the same way. Up, down to the minimum, and then back up. And here we go. Note that this has gotten taller. The amplitude went from being 1 to being 2, and it also went higher up. All of these points are higher up than they were before on the x-axis. Right? Whenever you're graphing either a sine or a cosine graph, you're going to be expected to have these 5 points at a minimum. The start and end of your period, the point that's halfway between the start and the end, the point that's a quarter of the way through, and the point that's 3/4 of the way through. All of our examples so far have been with the sine function, but even with the cosine function, you still have 5 points that you're going to highlight. The one at the beginning of the period, the one at the end of the period, the one halfway in between, the one 1/4 of the way in, and the one 3/4 of the way in. All right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. They're going to be different points, but you're going to have 5 points for each of those curves. And finally, let's go ahead and put one where everything is all together. And I'm going to ask you to try this one. We're going to go ahead and graph f of theta is equal to, let's do 2 sine of 2x plus pi minus 1. So go ahead and give this a try. Go ahead and use the 3 examples that we've seen so far to try to graph this. I would ask you start by graphing the original sine function. The f of theta is equal to sine of theta. Ooh, that should be a theta here, shouldn't it? And then modify that original graph to give you the graph of our new function. Note you're going to have a change to the amplitude, to the period. There's going to be a phase shift, and there's going to be a vertical shift. So go ahead and pause the video and give that a try. And when you have a result, go ahead and unpause the video, and we'll go through that one together. All right, so let's take a look. So let's take a look here. Let's start off by graphing just the basic sine function with no modifications, just f of theta equals sine of theta. And, well, we're going to start at the origin. We're going to go up to a maximum at pi over 2. We're going to come back to the axis at pi. We're going to go to the minimum of negative 1 at theta equals 3 pi over 4. And, well, that's not right. That should be 3 pi over 2, shouldn't it? There we go. And we go back up to the axis at theta equal to 2 pi. And you can connect these to form the, by now, very familiar looking wave. Okay, so we'll go ahead and compare this to the graph that we're about to form. So let's start off by looking and see where our beginning and our ending are going to be. All right. Here we have several operations. We have things in the argument. We have a multiplication here, and we have a subtraction here. If you think back to college algebra, you'll remember that modifications, transformations of functions happen following the order of operations, meaning this goes first, in parentheses, then multiplication, then subtraction. So that goes first. So the way we handle this is we're going to take this argument, we're going to set it equal to 0 to see where the beginning of our period should now be. And we're going to take this argument and set it equal to 2 pi to see where the end of our period should now be. All right, so let's go and do that over here. The period will start whenever this is equal to 0. I can subtract pi from both sides to give me 2 theta is equal to negative pi, and then divide both sides by 2 to give me theta is equal to negative pi over 2. Okay, so I know my period's going to start there, and I know it's going to end whenever this argument is equal to 2 pi. I can go ahead and subtract pi from both sides. 2 pi minus pi is just 1 pi. So 2 theta is equal to 1 pi. And now I have to divide both sides by 2. So this will be theta is equal to pi over 2. All right? So that means that our graph is going to now start where theta is equal to negative pi over 2. So back over here. Let's go ahead and put that in. And it'll look like this. So our graph will start back here and it'll end over here. All right? Or at least the central period of our graph will be transformed to start from here and end over here. Now, I'm not going to put the points here yet because I don't know exactly where they belong. Notice I have other transformations to worry about. So for right now, I'm just going to put in pencil here so that I can erase it later. I'm going to put a line here because I know that this point is going to move back here somewhere, but it might be higher up or lower down. And same thing, I'm going to go ahead and put a line at theta equals to pi over 2. If you don't want to put a line, that's fine. You can just imagine where it is or keep track of where it is in your head. But here, I'm going to go ahead and draw it because, well, you can't see what's in my head. So I have to physically draw that out. Theta is equal to negative pi over 2 and positive pi over 2. So I know that my period will begin somewhere over here and it'll end somewhere over here. Okay, that will come to over here. All right, but now we have some other changes to make. This will affect the amplitude. It'll affect how far up and down we go. This will give us a vertical shift. In this case, that's -1, so the whole thing will move down 1. What we want to do is we're going to use that to keep track of where these points on our axis should go. So -1 means these points should all move down 1 step. Okay, so now I know where my points on my new period should be, at least these 3 points. This point is going to be over here now. All right? The period should now start at negative pi over 2. But because of that -1, it's going to go down here. All right? This tells me that theta should be negative pi over 2 when my period starts. And because of that -1, this is going to come down 1 step. This point right here is going to be the end of the period. Okay, so that's going to exist over here somewhere. Oh, but again, because of the -1, it's going to be 1 step below the axis. So this point moves back and down 1 step because of that -1. And this point comes back and then down 1 step because of that -1. Now remember, halfway in between these two endpoints, we're going to have another point that is this point here. All right? Halfway in between the two endpoints, we have another point on this baseline on this axis. So halfway in between these two endpoints, halfway between minus pi over 2 and positive pi over 2, we have this point on our baseline. All right. That 2 is giving us an amplitude. Okay, well, here's our baseline. And our amplitude simply says how far up or down we're going from our baseline. So from here, from this line at -1, we're going to go up to our maximum, and our maximum is 2 steps above this baseline. All right, so halfway in between here and here, I'm going to find my maximum, negative pi over 4, and my maximum will be 2 steps up from this line. So 1 step, 2 steps. There we go. There's our new maximum, from -1 to 0 to +1. And now our minimum will be 2 steps in the other direction. Halfway in between here, halfway in between 0 and pi over 2, that's pi over 4. And now I'm going to take 2 steps down from there to find my minimum. And again, I know that because of the amplitude. So now I connect my dots in the typical smooth curve in this wave form that we've seen over and over again throughout this section, throughout these sections. And that's our graph. So this right here is f of theta. Here I can go ahead and erase that line. Those lines aren't part of my graph. They were just there to help me keep track of where the period should begin and end. And there we go. Compared to the original sine of theta, this is now significantly narrower, and that right there changed the size of the period. Everything's moved over some. This caused the phase shift. I have a different amplitude. Things are now taller than they used to be, and this caused a vertical translation. Everything's a little bit lower than it used to be. These points here have moved down a step. And there's our graph. And that is it for these sections. Note that all of our examples have been done using the sine function. There in the homework will be a few problems that involve the cosine function as well as the sine function. And remember, nothing about what we've done here is any different. The only difference will be in the initial function. Here in every one of our examples, we started with this curve in red and then modified it. If instead of sine we have cosine, you would start with this as your original function to modify. But all the modifications would be done the same way. The number in front would give you the change in the amplitude. This number here would give you a vertical shift. And these numbers in here would tell you where your period should begin and end. But again, 0 and 2 pi, 0 and 2 pi. So nothing computationally will change, just what the original curve will be. And that is it for this section. these sections. If anybody has any questions, comments, or problems, please make a note of those and reach out to me. Come talk to me during our next meeting or my next office hours. All right? You know how to reach me, and I hope everyone has a nice day.